let's do some examples with inverse Laplace transform. So in my last video, we saw it where we had our lowercase f of t, right? And we took the Laplace transform of that, right? We looked at our table, and this would produce our capital F of s, right? So our integral, right, that Laplace transform of f of t, that gives us a function in terms of s. And we just kind of use our table to manipulate it, get the solution there. So this time we're going to go backwards. We're going to start at f of s and try and go back to f of t. So if we go from left to right, we have to take the Laplace transform. That must mean going right to left, we have to take the inverse Laplace transform of f of s, right? And that's going to give us our f of t. Okay, so we're going to use the table that we created before to do these questions. That's why it's kind of helpful to have a table. So let's just say our capital F of s. So when we take the Laplace transform of some function f of t, right, the result that we get is 1 over 3s minus 1. So what is the original function that we took the Laplace transform of? Right, well, 1 over 3s minus 1, let's look at our chart and see if we see anything like that. So here we have 1 over s minus a constant, so this could be 1, but we have 3s minus 1. This is just 1 over s. That's probably not going to help us. This is a factorial with n. This is s and b squared. Same with this one. So our best bet for what we have as of now is 1 over s minus lambda. But the only thing is, we have 1 over 3s minus 1. So what we want to do in this case is we just want 1s. And what we're going to do is, if we factor out a 3 from 3s, right? So if we have 1 over 3 times s minus, this s is just 1s now, right? And this 1/3 becomes a constant. So when we factor out a 3, this is also going to become minus a third, right? Because we have to kind of expand this 3 into both of these to get this back. But if we factor out a 3, right, now we have this part as a constant. So it equals 1 over 3 times 1 over s minus a third. And this is the exact same thing. So it's an equivalent way to write the equation, right? Except now we just have a constant, which is fine because Laplace transforms are linear. We can factor out a constant, right? And now we have it in the form 1 over s minus a constant. So let's just go back up here. 1 over s minus a constant, that's going to be e to the lambda t, right? So if we're starting on this side now, right, we're starting on this side, taking the inverse Laplace of that. Our lambda is just a third. So our answer is going to be lowercase f of t, and our lambda is going to be a third. So it's going to be e to the lambda t, so e to the 1/3. So I'll write the inverse Laplace of f of s. That's e to the 1/3 t, right, times 1 over 3. So I'm just going to write e to the 1/3 t over 3. Okay, and this would be our answer. So if we were to go the other way, if we were to take this lowercase f of t, take the forward direction, like the normal Laplace transform of this, we would get 1 over 3s minus 1. Okay, let's do another example here. Let's say we had capital F of s, right, was equal to 5 over s to the 6th, right? This would mean that our f of t is going to be equal to, if we have 5 over something, that's just like 5 times 1 over that, because the 5 joins with the 1. So lowercase f of t is going to be 5 times the Laplace transform of 1 over s to the 6th. Okay, if we have 1 over s to the 6th, well, let's just see here. If we're kind of looking at this row right here with the inverse Laplace transforms, that's where this is going to come in handy. So remember I think it was 2 videos ago, I said you're going to see this form a lot more than this form in nature. And this is an example where you have 1 over s to the power of something. In this case, it's 1 over s to the 6th. That means n is 6, so it's going to be t to the n minus 1. So t to the 6th minus 1, t to the 5th, over 5 factorial. So this is going to be t to the 5th over 5 factorial. So I'll write equals 5 times t to the 5th over 5 factorial. Okay, and you'll notice that if we have this 5 out over here, right, and we have 5 factorial over here, 5 factorial is like 5 times 4 times 3 times 2 times 1. The 5s are going to cancel. So this is really, oh, we'll actually write it horizontal here. T to the 5th over 4 factorial, because the 5 is just going to go away. And 4 factorial, let's see, that's 4 times 3, which is 12, times 2, which is 24. So t to the 5th over 24. Okay. And that's that one there. And the next one, let's do, so capital F of S, right? Once we do the Laplace transform of our lowercase f of t, we're going to get 1 over s squared plus 2, let's say. Okay, so this is similar to what we saw before, right? This is a time where we see this more in nature than b over s squared plus b squared, right? Because if we just had this form of the function here, we wouldn't be able to solve this because the square root of 2 isn't 1, right? It's like 1.3. So we're going to use this inverse Laplace transform, right? And we're going to say the inverse of this, right? That's going to be 1 over b sine bt. Okay, so if, let's see here, we have 1 over s squared plus 2. So here's our 1, here's our s squared plus 2. Well, if 2 is b squared, that must mean that b is the square root of 2. So this is going to be 1 over root 2 sine root 2t. So I'll go inverse Laplace transform of f of s. That's going to equal f of t, right? Lowercase. It's going to be 1 over root 2 sine root 2t. And again, what this means is if we take this lowercase f of t and we apply the forward kind of facing Laplace transform, we would get our uppercase f of s to be 1 over s squared plus 2. Okay, and we can rationalize this if we want, right? This could be root 2 over 2 sine root 2t. It's all the same thing. Doesn't matter a whole lot. And it's kind of a coincidence. Root 2 over 2 is, that's the cosine and sine of pi over 4, but that's kind of just a coincidence. Doesn't really matter. Now the next one we're going to do, let's say we had capital F of s to be equal to 4 over s plus 1. I think at this point you kind of get the idea. Minus 6 over s squared plus 7. Right, minus 1 over s cubed. Okay, so the inverse Laplace transform of f of s, that's going to equal, well, remember, 1 over s minus lambda is the Laplace transform of e to the lambda t, so the inverse of this must be 4 times 1 over s plus 1, so 4 times e to the lambda t. If this is plus 1, it's usually 1 over s minus lambda, so this must mean lambda is negative 1, right? Because s minus negative 1 is just s plus 1, which is what we have. So lambda is negative 1. We factor out the 4, so e to the negative 1 times t, so e to the negative t, right, minus this here. We have 6 on the top, 7 on the bottom. This is where we use this inverse Laplace transform. So this will be 1 over b sine bt. If this is s squared plus 7, that means that b squared is 7, therefore b is the square root of 7. So it's going to be 1 over root 7 sine root 7t. And remember, we have the 6 here as well. So it's 6 times 1 over root 7, which is just 6 over 7. 6 over root 7 sine root 7t. Right? Plus, sorry, this is going to be actually minus. I had it as, right? Yeah, we can go plus or minus. Let's go minus. So minus, this is 1 over s cubed. If we go back to our table, right, 1 over s to the n, that's kind of the one we're looking at. 1 over s to the n, that means n is 3, so it's going to be t to the 3 minus 1, so t squared over 2 factorial. So 2 squared over 2, right? And that kind of resembles the integral of t dt, right? 1/2 t squared. We see that a lot in Laplace transforms as well. So these are some examples with inverse Laplace transforms. And honestly, that's probably going to conclude the introduction of Laplace transforms. Now we're actually going to use them. I know you've all been waiting. In the next video, I'm going to actually do some differential equations using the Laplace transform as an operator, right? So if we have an equation, we can apply it on both sides. That's totally valid. And yeah, you're going to see some pretty cool stuff come out of it. So I look forward to that. See you there.